So back to what I'm going to be talking about. So I'm talking about bisphenols in leather. If you've been involved or to any leather conference, you've probably heard more about this than you've cared to, but hopefully what I'm going to talk to you about is a bit different from the way that a chemical company would look at it, with this, where they're seeking to reduce the bisphenol content of their chemicals and therefore for leather. But here I'm looking at how the bisphenols are actually transferred into leather. So first of all, I'll talk about bisphenols, what they are, why we're bothering to talk about them, why is it something that's relevant, before going on to talk about my sorts of results. This is work that I've done together with Dr. Stefan Davis, supported me in technique development as well. It says Associate Professor, Leather Technology and Sustainability. This is as of last week, because I now have to return back to being a lowly doctor. So now Dr. Andrew Ballantyne. I have now left ICLT, but if you wish to contact me, I've included my personal email address. You can contact me on LinkedIn as well. Please don't be a stranger. I'm happy to answer any questions and have interesting discussions about this and many other topics as well. I'm going to start here. This is a bottle of water, which if you go to if the conference was held at the university, they probably would be hosting these types of bottles. There's lots to like about it. First of all, the plastic comes from waste sources. I think in this case, it's made from waste food starch. It's also encouraging you to reuse it. So all these really great approaches to sustainability. Obviously, you can't repair the bottle, or you could try, but you might find it pretty difficult. I appreciate all this wording is quite small, so either use a magnifying or just accept what I'm telling you at this point. And even your photo wasn't that high quality, so you see it's quite hard to get an actual cutout. The thing that I want to highlight from this is this little bit that I've blown up here, where it says BPA free. And this is where it all starts. So it's BPA free. What does that mean? So it's easy for us to think, as the leather sector who's not got as strong a voice as other sectors, that there's a target sometime, or we're being targeted. But actually this is relevant across a whole range of industries, and I'll demonstrate that as we go through the next few slides. So it's already on our drinks bottles, and it has been for quite a long time as well. So bisphenols. This is what BPA is. Bisphenol A. It's one of the many types of bisphenols that you might see. These are compounds which are composed of two phenolic groups that are linked together in some way. Example of BPA is phenol, which is linked together in a condensation with acetone. That's about as much chemistry as we're going to get today. It's often called a plasticizer. It's not true, apart from very niche cases. They're there as a starting material, as they are in leather making as well. And their consumption is huge, 7.2 million tons annual production in 2022. Yeah, so that's a massive scale, much more than you're going to see used in the leather industry as well. And there's two main types that can be found in leather: bisphenol F and bisphenol S. Bisphenol F is a condensation of two phenols with formaldehyde, which is, this is phenol reaction with formaldehyde. Condensation is how you produce phenolic syntans. And BPS, bisphenol S, where you have this sulfone in the center. This is the starting material from which sulfone syntans are made. So there's, in the case of BPF, that's present as an intermediate product, impurity, it's not tanning. It's there as an intermediate product in the manufacture of phenolic syntans. BPS is the starting material that remains there in the final product, if it's still there in the final product, of course. To give you an idea about how common these things are, we've got a value for BPA in a few slides, but for bisphenol S, about 81% of people will test positive for this, maybe a bit higher in this room, I don't know. But it shows you the range of different products that this must find its way into in order to be that kind of ubiquitous. So about 81% of us will test positive for it. So why is it an issue? Well, one thing is, say, the petrol-based, the synthetic chemicals normally, but these are synthetic chemicals, but also they're kind of related to the endocrine system as well. So just to briefly, I mean, I'm no biologist, but to briefly touch on what the endocrine system is, it's present in a number of different areas throughout the body, and the endocrine system are the glands and organs that make hormones and basically regulate the way that our body is performing. Yeah, so and see that's really pretty vital to our overall health and to ensure that we maintain our health and things are operating in an effective way. Yeah, so the hormones that are generated, released into the blood, and then they travel to tissues and organs all over the body. So it's a pretty central and kind of essential process in order for our just general maintenance. And bisphenols are potentially, or they are, so not potentially, they are an endocrine disruptor. What that means is it's something of external origin which interferes with synthesis, secretion, transport, binding, action, the action, elimination, basically the pathway of which a hormone is generated and is released into the body, and it ultimately does its job when it gets to when it's going to regulate certain things. So that's it's going to interfere with this process in some way. Actually, this is a bit like drugs as well. So it's exactly the way. So I have hay fever. So it's kind of the way hay fever drugs work as well, or histamine works. So it's not a completely unusual process. But if you have something which is external of origin, which isn't necessarily a natural thing, then there's certainly the potential that is going to interrupt and disrupt the standard way in which our body is going to be operated. This brings us on to bisphenols and how they interact with the endocrine system. So bisphenol A is what's known as a xenoestrogen. There's lots of research on this. It's fairly conclusive. I think we can say absolutely, or from what I've read, we can say absolutely that it is a xenoestrogen. It means that it acts and it exhibits estrogen-like effects on the body, particularly like estradiol, which is in green here. So bisphenol A is in blue, purple, and then estradiol is in green. So I don't particularly like this diagram because it's a 2D representation of something which is actually 3D, but you can kind of see how they overlap a little bit, which means that these sorts of bisphenols are suspected to behave a bit like estrogen. So estrogen is a really important hormone for management of sexual health, but amongst many other types of things in our development, in particular as you are growing up and we're going through lots of developmental changes, from young age up to maturity, then this can have many implications in the way that people grow and develop, and which can be significantly consequential. So why is this something which is really important now? It's actually less important now if you're involved in this and you know that it's been withdrawn. But the EU is labeling these as a substance of very high concern, or was intending to label them as a substance of very high concern, applying to bisphenol A, like bisphenol B, which is, we'll ignore that for this presentation, bisphenol F and bisphenol S, which are the two obviously that are very relevant to leather manufacture. And we're going to limit them really quite significantly. You'll see this compared to the actual typical values you'll see in leather, from 2025 to 500 milligrams per kilogram in leather, and then from 2030 to 10 milligrams per kilogram of leather. This is now withdrawn, but it's probably going to be resubmitted at some point. But in addition to that, it's finding itself onto restricted substances list anyway. So even though the regulations have been withdrawn, it's actually becoming something which is important for leather manufacturers to have to meet anyway. That's a background. We've explored what bisphenols are, the ones that are present, that may be present in leather, and why that's something which we're interested in looking at. So now I'm going to talk about this work. So this is, so as opposed to looking at the component, the quantities and chemicals, here I'm looking at the transfer from the bisphenols into leather and how tanners might actually think about changes to their approaches to mitigate or minimize the bisphenol content in leather. So it's basically breaking down into what is the bisphenol content of a random array of replacement syntans. How do they transfer into leather? So what quantity, how do the quantities in the chemical relate to the quantities in the leather? Is it the same across the whole hide? Obviously, leather is, yeah, it's not uniform across the entire hide. We want it to be as uniform as possible, but the reality is the skins are not. And then also, can you change how you make leather so you can reduce the bisphenol content? We followed this very typical crusting process, going from wet blue to crust. Yeah, very try to keep it as basic as possible. First of all, to reduce the interference in the measurements, but also to have it kind of relevant to an actual leather manufacturing process. And then we test this using HPLC, the second mention of HPLC today. So to separate out the different components when we extract the leather, and then and measure them using what's called a diode array. So look at the intensity of the absorption, tells us about the concentration in the leather. So kind of not so much interest, I think, is what is the bisphenol content of various chemicals, because I'm not labeling the chemicals and saying what they are. Some of these were specifically defined as, you know, low monomer or low bisphenol content. So it's not fair to actually label them anyway. But those which are sulfones, the ones that contain bisphenol S, contain much higher concentrations of bisphenols than those of the phenolic syntans. So so bisphenol S could be in the range of tens of thousands of milligrams per kilograms, whereas bisphenol F is maybe 400, 200, around about that sort of range. So a big difference in the relative concentrations. Something also just to identify, it wasn't always easy to identify which of the bisphenols would be present by looking at the technical data sheets. So it's maybe something which could be addressed, but that would help tanners, you know, review and identify what chemicals are best for them. Although I know that there's always a very good back and forth between tanneries and the chemical manufacturers. Then, as I said, the last slide is less important. You know, what is from this study's perspective, what is the concentration of bisphenols in the chemicals? What I think is more interesting is seeing how they transfer into leather and then see where they're distributed as well. So here we have two different trials, one looking at phenolic syntans, and the other looking at, which is trial 1. Sorry, wrong way around. One looking at sulfone syntans, which is trial 1, and one looking at phenolic syntans, which is trial 2. And just as you would expect, sulfones, which have a higher bisphenol concentration in the chemical, result in levers which have a much higher bisphenol concentration as well. It's roughly 20 times lower than that of the chemical. In this process, it depends how much you're adding, how you run the process, but that's in this example. And then the bisphenol F was roughly similar to that, although we found that sometimes there was interferences in the measurement, which made it harder to get an accurate value for that. What I also think is really interesting about this is if you look at this graph, let's look at the top one. The official sampling position always has, in my measurements, a lower bisphenol content than either the belly or the neck. So if you're taking a sample and you're trying to test whether it's within specifications, and you take the official sampling position, then that's probably, you're taking it from the place that is likely to have the lowest bisphenol concentration. So something to bear in mind. Whereas if you have a shoe, let's say if you're taking a shoe you're taking a shoe and you test the bisphenol concentration of that, then depending on where that panel was taken from, it might have a higher bisphenol concentration than you actually thought when you tested it in the first place. It could be up to about 10%, 12% higher if you were taking from the belly or from the neck. The belly typically had the highest bisphenol concentration. I think probably the most interesting results of that I found was from demonstrated here. So there's quite a lot of graphs, there's quite a lot of different bars. So I'm going to explain what is shown here. The important thing to look at is where it says crust. Yeah, that tells you about what is the bisphenol concentration in the crust. And what I've done here is look at 4 different processes, all based off that standard one which I showed in the earlier slide, where I've made some changes. I've got the standard process, which is the second bar, the red bar that you can see, and then I also have ones where we've added the syntan into the neutralization bath, one where we've done fixation at the end of retanning and then washed and then done fat liquoring, and then one where we've done the retanning and the fat liquoring all in one bath and fixed at that point. So basically the residence time of the tanning agents inside the bath is longer. And what you can see quite clearly is actually there's quite a big difference in the final bisphenol concentration of the leather depending on how you do this process. Okay, so looking at bisphenol S, the top with the crust, if you add the syntan into the neutralization bath, I've got a table here, let me put that up. If I add it into the neutralization bath, then actually that's about nearly 20% lower bisphenol content than it is for the standard process. Whereas if you do everything in one bath, then that can increase the bisphenol concentration by about 20%. So you can look, depending on how you're making your leather, then actually you can have almost a 40% difference in the bisphenol content, depending on how that you have made it, which I think is fascinating. And the rest of the parts of the chart are where I've taken samples at different stages and measured the bisphenol content of them. And you can see how it tracks. When if you're adding your syntan into your neutralization bath, then of course it's going to be drained, maybe washed. Then it's got the retan bath, drained, maybe fat liquors. Yeah, so all these different stages means it can start to get washed out. Something I also think is really interesting is that just by fixating, so we say that the bisphenols aren't tanning, but just by having a fixation, adding some acid into the bath at the end of retanning, actually increases the fixation of the bisphenol compounds quite a lot. So just like reducing the pH increases the affinity of the tanning agents with collagen, it's doing the same thing for the bisphenols as well. Okay, so it's not so many results, but so they take a little bit of time to explain, and hopefully that's interesting when you're thinking about how you might design a manufacturing process to make low bisphenol leather. Yeah, exactly. So I think what we found out is HPLC, certainly in this case, was an highly effective method for detecting the bisphenols. And all of the replacement syntans that we studied did contain some, although some were very low. Results question whether the OSP is the best place to take a sample from for bisphenol measurements, or whether you should apply a factor based on from that to ensure that your leathers are going to be sufficiently low bisphenol concentration, and that you can get actually quite a significant reduction in bisphenol content just by changing the way that you make the leather.